For decades, the expectations seemed straightforward. Gravity pulls matter together, so the expansion of the universe should gradually slow down. Maybe not stop, but lose speed over time. Then two separate teams set out to measure it. They looked at distant exploding stars, ancient flashes of light scattered across deep space. By comparing how bright those explosions appeared with how far away they were, they expected to see a universe whose expansion was easing off under gravity's pull. Instead, the numbers pushed in the opposite direction. The farther they looked, the stranger the pattern became. The expansion was not slowing down. It appeared to be speeding up. That result created an immediate problem. The experiment was supposed to measure how much gravity had reduced the expansion rate. Instead, the measurement suggested gravity was losing the contest. Both teams checked their data. The expectation remained the same. The observations did not. A prediction that had seemed reliable now sat in direct conflict with what the universe was actually doing. Either the measurements were wrong, or something across cosmic distances was overpowering gravity itself. The easiest escape route is still available. Maybe the measurement is wrong. A subtle error in the data. A flaw in the calculations. Some hidden problem buried inside the observations. If that is true, then the strange acceleration disappears and gravity returns to behaving exactly as expected. So the result is tested again. A separate team examines a different collection of distant exploding stars. Different observations, different analysis, a different path to the answer. The expectation is simple. If the first result came from a mistake, the second result should drift somewhere else. It does not. The new measurements trace the same pattern. The distant explosions appear where they should not be. The expansion still looks faster than expected. The contradiction survives the second attempt. Now the problem changes shape. The anomaly is no longer trapped inside a single set of observations. It exists in multiple places at once. The easiest explanation begins to disappear. A mistake can explain one result. It becomes much harder to use the same explanation when independent teams arrive at the same conclusion through different data. The prediction remains unchanged. The observations remain unchanged. And with every repeated measurement, confidence shifts away from the error and toward the possibility that the universe is actually doing something unexpected. If the measurements are right, then the real mystery is no longer whether acceleration exists. It is what could possibly be causing it. The measurements refuse to go away, so attention shifts from the data to the universe itself. If the acceleration is real, then something physical must be producing it. An older idea, mostly left in the background for years, begins to return. What if empty space is not truly empty? Imagine space stretching outward in every direction while carrying a small, built-in push of its own. Not matter, not galaxies, not anything visible through a telescope, just a property of space itself. Suddenly, the observations begin lining up differently. As space expands, that outward push remains part of the picture. The distant exploding stars still appear where they were observed. The acceleration no longer stands alone as a contradiction. For the first time since the measurements appeared, theory and observation can occupy the same room. The universe can keep accelerating, gravity can keep existing, and the conflict between them no longer looks impossible. The idea is not proven, but it changes the shape of the mystery. The acceleration no longer looks like a measurement problem. It starts looking like a feature of reality itself. For years, the question had been whether the observations could be trusted. Now a different possibility begins to emerge. The observations may be correct, which means the universe is not behaving differently than expected because gravity failed. It is behaving differently because something else is participating in the expansion. The mystery has moved. It is no longer hiding in the data. It is hiding in the universe. If that is true, then a new question immediately follows. How much of the universe does that hidden component actually account for? The new idea seems manageable at first. a small outward push hidden inside space, just enough to explain the acceleration, just enough to repair the mismatch between prediction and observation. At first, it looks like a minor adjustment, a small correction added to an otherwise familiar universe. Then the numbers begin getting larger. Not the acceleration itself, the role this hidden component appears to play. Every new measurement pushes it further from the edge of the story and closer to the center. Then more measurements arrive. Astronomers begin comparing different observations of the universe. They examine how expansion changes across cosmic history. They measure large-scale patterns. They test the numbers from multiple directions. And the answer keeps pointing the same way. The accelerating component is not showing up as a minor correction. It keeps appearing as something much larger. What looked like a patch begins behaving like a foundation. The more observations are compared, the harder it becomes to treat the acceleration as a secondary detail. The picture changes. The visible universe begins shrinking. Not physically, conceptually. Galaxies, stars, planets, and everything seen through telescopes start looking less like the main story and more like one layer of a much larger picture. The measurements keep suggesting the same unsettling possibility. The familiar universe may represent only a fraction of the total picture. The things people can see through telescopes may not be the dominant influence shaping cosmic expansion after all. What looked like a small adjustment at the edge of the problem begins spreading across the entire universe. The outward push is no longer sitting quietly beside gravity. It appears woven into the behavior of the cosmos itself. That creates a new kind of pressure. The original crisis was simple. The expansion rate did not match expectations. Now the measurements and the theory can coexist. The acceleration has a place in the equations. The observations fit together far better than before. But the solution comes with a cost. The more important this accelerating component becomes, the harder it is to ignore a different fact. Its effects can be measured. Its influence can be tracked. Its fingerprints appear across observations. Yet the source remains unconfirmed. Cosmologists can increasingly describe what it does. They still cannot say with confidence what it is. But the thing producing them still refuses to appear directly. The universe behaves as though this component is real. The measurements repeatedly support its presence. But knowing that something affects cosmic expansion is not the same as knowing what it is. The problem has not disappeared. It has changed scale. The original mystery involved the expansion rate of the universe. The new mystery involves the universe itself. The more successful the measurements become, the harder it becomes to ignore what they imply. Cosmology can increasingly measure the effect with confidence, while the thing producing it remains unknown. And if most of cosmic behavior depends on something unknown, what exactly does that mean for our understanding of the universe? The measurements continue, decades pass, the acceleration remains. Instruments change, telescopes improve, entire generations of observations come and go. The anomaly survives all of them. New observations arrive. The calculations improve. Telescopes look deeper into space and farther back through cosmic history. Yet the same pattern keeps appearing. The universe is not simply expanding, the expansion is accelerating. What began as an unexpected result in distant exploding stars now survives repeated testing across modern cosmology. The effect remains visible no matter how carefully the measurements are refined. That creates an unusual situation. One of humanity's most successful descriptions of the universe depends on something that is not observed directly. Its presence is revealed through behavior, through motion, through the way cosmic expansion changes over time. The effect appears consistently. The cause does not. The observations fit together. The model continues to work. The acceleration remains part of the picture. But the deeper question has never fully disappeared. What is producing it? The original goal seemed simple. Measure how much gravity had slowed the expansion of the universe. Instead, the measurements revealed something else. The cosmos appears to be accelerating under the influence of a component whose nature remains unknown. What began as an attempt to understand the universe's expansion became evidence that a significant part of cosmic behavior may depend on something that has never been directly identified. The discovery did not make the universe simpler, it made it less complete. The universe still expands. The measurements still work. The models still describe what is observed. Yet one of the most important influences on cosmic history remains unidentified. We measured the effect. The cause remains hidden. The more accurately we map the universe, the more clearly we can see the outline of something we still do not understand.